Perfect.
There,
It's all good?
Full screen, perfect.
Yes.
All right, so hello everyone. We're gonna shift gears a bit, go back and look at the technology of ore sorting, which is what we're gonna be modeling. Bit about myself, 20 years in the mining industry. Most of it has been operations. The last 5 years, I've done a lot of ore sorting projects, about 50 of them. Design, we've built some, really been on the forefront of pushing this technology. Right now, I'm Vice President Mineral Processing for ABH. ABH is a completely independent engineering company, so we don't have our own technology. We use all the vendors' technologies and we work with all of them, and we believe each one has its own application. As we go, just type in questions and someone will read them to me. So feel free to interrupt, that's no problem. We've got a lot of stuff to cover, so let's jump into it. There we go. Yes, this is true. Mining, we in theory want to innovate so long as nothing changes, and that's been a problem that we've had for quite a while. Mining is a naturally conservative industry. You have to show some really compelling benefits in order to get people to change, and that's okay. So we just focus on showing those benefits. So we'll look at what is sorting, why we care about sorting, what are the benefits of sorting, and then that'll transition back into, now that we know sorting is a useful technology, how do we really model that properly? And we'll see some videos. We'll look at something we call profit recovery, which is one of the extremely simple metrics that we can use. We've got some examples from operations, which is always good. We'll look at a little bit of the testing that's required and talk about the need for modeling. So this is how we used to ore sort. This is an optical system. You look at the rock. If it's good, you send it to your mill. Very useful, very effective as far as optical goes. It's based just on surface, which is limiting. So you don't have any of these fancy X-ray technologies looking at the entire rock. You've got no elemental analysis potential, but still, it was fantastic for its time, and even today, this is still sometimes used. But we've come a little further. So this is, let's see if we can play some of these videos. Now, none of these are my technologies, these are all the vendor technologies, but some of these animations are fantastic at explaining how it works. So in this case, little black cubes and little white circles represent ore and waste. And they're scanned, and as it flies off the end of the conveyor, a whole bank of diverter jets divert it. And the stuff on the left represents maybe 15% of your total material. That's the only ore. Everything else is garbage. So in this operation, this was a tungsten operation, everything was worth throwing away except for those, 15% of the rocks that were worth keeping. This is my first silver operation, taken on an old iPhone 5. And again, here we're seeing 10 to 20% mass is containing the vast majority of the silver, and it's containing all of the silver that's worth recovering. Everything else is worth throwing away. This is another technology, COMEX. And this is pretty typical of the particle sorting technologies. You've got a feeding system which spreads it out over the entire width of the conveyor. Often these will be 1 to 2 meter wide conveyors. Here they're showing an X-ray system. There's your bank of nozzles. as your particles fly down the conveyor. These things these days moving 2 or 3 meters per second, the conveyors. Each particle is scanned individually and diverted based on the sensor. Now that in this case, we've got X-ray transmission. You could also have XRF scans, which is more of an elemental analysis, optical, laser, infrared, ultraviolet, electromagnetic. It's quite the list for what particle sorting can do. This is a Tomra style machine. It's got some music, which is nice. Hopefully you can hear that. So this one's dual energy X-ray transmission, which is probably the most popular scanning technology. It compensates, sort of like a bone density scanner, compensates for rock size to give you a relative density. So as these rocks fly past, each one is analyzed. The computer makes a decision saying, oh, this one's worth keeping, this one's worth throwing away. And as they fall off the end, they're diverted into the proper bin. And should note, if the average density where you that used to be used in terms of things like dense media separation, which I still use sometimes. But this can look at more of the density profile. So just because the average density is low doesn't mean it's necessarily waste. There could be a little spike in the high density pixels. So you want to keep track of that and use all the data available in your analysis. This is a Rados machine, which is nice because it's the very, very accurate XRF technology. So if you've got a little silver operation, you want to detect your silver directly, this can do it, which is amazing. It's channel limited, which means you're not going to get hundreds of tons per hour, but you will get a very, very good XRF reading on this. And they actually make double bank diversions now. So this is the only machine that can do a 3-product sort instead of a 2-product sort. And nice thing about XRF is, you know, all the rocks can be the same color and they can all have similar characteristics, and the elemental analysis gives it away. Very, very common with gold and platinum operations where you're looking for some sort of indication of where that gold is. You can't detect it directly. If XRT doesn't work, if laser doesn't work, you know, you don't have sulfides, you don't have quartz, this machine will usually give it. Usually works. This is RedWave. Again, it's very similar to the others. Very large capacity machine. Okay, now we're getting a little different. So what we've been looking at so far is particle sorting, where each individual particle is analyzed and a decision is made based on that. If you've got an open pit, you're doing 100,000, 200,000 tons per day. Particle sorting might not be the right choice. Maybe you want to do bulk sorting. Bulk sorting is great because once you set it up, it's pretty much free. All you've got is a sensor and a diversion system for the entire conveyor. So in this case, we've got prompt neutron gamma activation, which is a lovely technology, where you've got a nuclear or electric source. It's emitting neutrons through your conveyor and through your material on your conveyor. It comes in contact with individual atoms, say copper. It excites that copper atom. The copper will then emit a gamma ray very specific to that element. So you've got a little spectrograph. and you can look and see the peaks where the copper is. You can measure that and get an idea of how much copper or lead or zinc, et cetera, is on your conveyor at any given time. Very handy because it can detect a lot of light elements where XRF can't. Also, it's very, very cheap to run once you've got it set up. Downside is you're diverting a large amount of material at once, either to product or rejects. So the grade recovery curve isn't quite as sharp as particle sorting. But again, if you're running a huge open pit and you can boost mill feed grade 10%, that's a huge win. So worth thinking about. Now this is MineSense. This is XRF, but on a shovel-based system. So each scoop falls into the bucket and gets scanned and gives you an idea of what the grade is.
And 2 channels of electromagnetic sensors.
So you're able to do a scan based on each individual scoop. So heterogeneity is sort of where the opportunity for ore sorting is. And it's a sort of thing that hasn't been measured very often before. A lot of places say, oh yeah, we don't have a lot of variability in our ore. And then we do a test on a particle by particle basis, and there's huge variability. Most of the time, we're looking at about 50% of the ore in undiluted ore blocks. Usually about half of it is worthless. You're losing money running it through your mill. Now, if you've got a little underground operation, maybe it's 80 or 90% waste. You've got a big porphyry copper, maybe it's only 40%. But it's always more than you'd think. The pit assays and the drill core assays give you an idea, a flavor for it, but it's always more variable than those indicate, because what we're sorting is 1-inch material, 4 or 5 centimeters. No one does assays at that level. So test work is always a good idea, just to see, let's try to quantify the potential. So we'll take a quick look at some of the different sensor types here. Bottom left is a Japanese mining company that still did hand sorting a few years back. I don't know if they still do. Top right is a 32-pack of ore sorting machines. This wasn't built, but this was a design done. So those machines do 200 tons per hour. There's 32 of them. This is a pretty serious capacity for processing on a particle basis. So this is the workhorse of particle sorting, dual energy X-ray transmission, where each particle is scanned with dual energy X-rays, and it gives you a wonderful relative density of each rock. So if you've got sulfide associated with gold, you've got any sulfide deposit of any kind, this is going to be the first thing we try. Extremely effective, an extremely good amount of data coming out of this. So using some of the AI and some of the smarter algorithms, there's a lot you can do with this data. It's very hard to hide sulfides in these rocks. So this works most of the time. XRF is a surface scan system. So it looks at just the surface of the rock because it doesn't penetrate, but it gives you elemental results. So you can, a lot of times we've looked at, so the example here, we look at copper, zinc, titanium, and iron. Those were indicating where the gold was and where the gold wasn't. So based on those, we could make a good estimate on how much gold we thought was in that rock and whether it was worth keeping. We also do a lot of ultraviolet, color, and infrared. Definitely not as popular as it was 20 years ago, just because it has to compete with some of these X-ray technologies and the laser technologies. But if you've got limestone, you've got emeralds and rubies, these technologies are going to be useful. We do a lot of work in diamonds in terms of not so much the cleaning, but the pre-concentration. Can we reject granite? Can we do coarse stone recovery before it gets to the mill? Because you don't want to smash those big stones. And we'll use some of these for that, as well as X-ray transmission. Electromagnetic looks at the conductivity and permeability of each rock, which is very cool. Unless you have magnetite, I've never actually used this except deposits where magnetite indicates where the value is. This is going to be a neat one now. Laser-induced breakdown spectroscopy. This is a bulk technology. Sort of like XRF. We have a high-powered laser, vaporizes a little bit of rock, follows up and superheats that into plasma. The plasma glows in spectrums that indicate what the elements are. This can detect gold and platinum, which is fantastic. Being able to measure things directly, very, very nice. So we can say, hey, if there's any gold or platinum signals coming back, take it as ore. On the downside, we haven't got this for particle sorting yet. This is still a bulk sorting technology. Even still, very exciting. Also, a lot of the prompt neutron gamma activation is starting to be detecting gold at lower and lower cutoffs. Yeah, using a laser to vaporize rock is inarguably pretty cool. So this is shovel sorting. We saw a little bit of a video here earlier. Able to do very high tonnage. It's being commercialized at Highland Valley Copper right now, as well as a couple other places. It's one of the bulk sorting technologies, so it's not able to look at every particle, but once you've got it installed, there's no real cost for running this. A little light will beep and say, hey, this bucket you scooped, you thought that was ore, that's actually waste. And then it's up to you what you do with that information. You can have a, if too many scoops of waste go into a truck, you can send that to the waste dump. Or if you want to get really into it, you can have an extra truck available or an extra pile available where every scoop of waste gets tossed off to the side. This is PG&AA. We pretty much talked about this, so we can skip this over. So there's a lot of different configurations. I don't know how many of these we'll talk about today, but for particle sorting, you've got your gyratory or your jaw. You'll run it through a screen. Often you'll have, if you have the tonnage for it, you'll have two machines, one running coarse material, one running fines. Bottom size is usually 12 millimeters or so. As you get finer and finer, the capacity of your machine drops off pretty precipitously. So it's really not worth processing material that's extremely fine. There's other technologies I use for that. There's jigs, there's DMS plants, and of course there's flotation. So bulk sorting, it's nice and simple. There are some pretty serious things to think about, especially if you've got a brownfield operation. Your mill's already built. That conveyor tie-in is going to be tricky. So what we'll do a lot of times is just in time diversion, where we'll put the sensor right before your ore stockpile. And then as the ore falls off the end of the conveyor, we'll have something that'll, if waste is detected, a little flipper will flip out, catch that ore and, catch that waste and send it back to the waste pile. That way you don't have to break your conveyors, you don't have to deal with downtime. It's way cheaper than tearing it down and starting from scratch. Some other nice things about this, there's no screening involved. You analyze everything on the conveyor, so there's no free feed prep. It's just nice and simple. You might only get a 10 or 20% boost to your mill feed grade, but that's still not a big deal. And if you can do it for pennies per ton, well, that's great. We've talked about this. So you've got some questions for particle sorting. Do you want to crush your oversize? What is your bottom size? If you don't crush your oversize, what do you do with the oversized material? Does it go straight to the mill? Does it go straight to the waste pile? Lots of different configurations here. Excuse me. All right. I think we've looked at stuff like this already. We'll just skip over a bunch of that. All right, some of the benefits of ore sorting. Big one everyone thinks about is mill feed grade. So if you can throw away half of the mass that was heading to your mill, you can approximately double your mill feed grade. That's a pretty radical idea. And most places, if you can just boost it 10, 20%, and you're getting good recovery, that's enough for most people. But there's a lot of potential there. Some of the less direct things like less selective mining. So if you've got an ore sorter effectively rejecting waste rock before it goes to your mill, now you don't need to be as careful with your mining method. So cut and fill, maybe you don't need to worry about that anymore. Maybe you go open stoping. You're open stoping already, well, maybe that block cave is a possibility. So it lets you lower your cutoff grade, lower your dependence on grade control in the mine. You don't need to worry about blending anymore. You can set up the ore sorter to take care of all that stuff. So the guys in the mine can focus on tons because they love focusing on tons. Smaller tailings ponds. This is a big deal these days. We've got the potential to reject a lot of material before it gets to the pond. And if you do that, now your tailings pond is smaller and fewer lifts, less likely to fail. And that's a big deal. There's also a lot of cost savings because tailings ponds are expensive, especially when they get larger and larger. As the little pyramid of the dam is getting bigger. Greenfield, you can design this into your system. So instead of doubling your mining rate, maybe you make your mill a little smaller while you're at it. So you're saving CapEx as well as OpEx. The geologists really like this one, where if you can take a waste pile and process that and make money on it, well, that's actually ore. Therefore, if you can process waste, turn it into ore, well, you can lower your cutoff grade. So the deposit cutoff grade can typically go down 30, 40%, something like that for most of these deposits. Now, whether or not that has a big impact depends on the geology and the profile of the block model. But usually that can have a pretty big impact, especially if you're gold and the value of your company is very closely correlated to your reserves. Anything you can do to boost those reserves is going to be a good thing. Higher metal production, of course. Mill recovery improvement is a neat one. So as you're increasing your mill feed grade, there tends to be a corresponding increase in extraction recovery. And it's good to capture that early in the process so you can say, it might be an extra 2% mill extraction recovery, But that's still a good part of your case for ore sorting. Similarly, if you've got a sulfide deposit and you're running a sort, you're concentrating the high-grade material, tends to be softer, so you tend to have a lower work index going into your mill. So again, it's nice to quantify that if you can. Transportation costs, if your mine and your mill are separated by a distance, if you have satellite deposits, if you're looking at acquiring deposits some distance away and running it to your central processing facility, ore sorting can have a big impact there because you throw away the material before you've spent all that money transporting it. Also, we have looked at quite a few times putting it underground. So before you hoist the material or before you run it up the ramp, it could be put underground. Usually we end up deciding to put it on surface, but it is neat to look at the possibility of putting it underground. As we said, you can take waste piles, run them through a sorter. The sorter isn't limited by any conventional upgrade ratios. So it could take 1 out of 10 rocks. It could take 1 out of 20 rocks. There is no ratio. It's limited by the geology, by the grade of individual rocks. So if your waste pile is 0.2 grams per ton, but you've got mostly zeros and the odd 10 gram per ton, you can produce 10 gram per ton or 5 gram per ton concentrate from your ore sorting system. That's a possibility. We're going to be saving a lot of water, a lot of power, and a lot of CO2 by diverting material from the mill. That's just common sense. So before we were grinding this stuff up into sand, now we can say, well, look, there's no metal in all these rocks. Let's not grind them into sand. That's a pretty clear win. Profit recovery was something we looked at and we developed in order to really simplify the decision-making process. It's a new metric. It's very similar to the grade recovery curve, where you look at individual grades, they turn into an average trend line, except we've said, look, there's operating costs involved here. There's tailings costs. So you take the value of each rock and you subtract off the cost of processing, the cost of tailings. And now you say, well, now what does this curve look like? And all of a sudden, throwing away those worthless rocks is a benefit to your profit recovery. So let's take a look at some of these operations here. All right, so first one's Barrick. So this is the old grade recovery curve. And this is for an ore sort. So as you move from, let's say, from right to left across, you start at 100% mass pull. That is where everything that goes into the ore sorter is accepted and carries on to the mill. As you reject more and more material, you're moving from right to left, your recovery starts to drop because you start rejecting rocks that have some gold in them. In this case, we did a very good job of, the algorithm did a very good job of putting all the high grade on the left and all the low grade on the right. You can see it makes a few mistakes and the order isn't perfect, but still it does a pretty good job predicting which rocks have gold in them and putting them in the right camp. So we subtract off the operating costs, turn this into dollars, and you can see we started at about 50% profit recovery. As you throw away more and more material, you see we peak at around 91% profit recovery at about 25% mass pull. Very simple calculation. It just shows that, hey, look, based on these costs and this algorithm, there's a lot of potential here to run a sort and increase the profits. This is an example for El Gallo. Very, very sharp sort here. This was a silver operation. They always have lovely, lovely sorts. So the algorithm did, again, a great job saying all of these rocks are probably worthless. And it was correct. and these rocks have high grade, and it was correct. So you subtract off the profit, and it goes from 70% up to, oh geez, 98% in this case. So vastly higher mill feed grade, lower costs. It's lovely. This is a new gold deposit. So here it's not quite as sharp, not as black and white for a grade recovery curve, but then we look at the profit recovery. You subtract off those costs, and all of a sudden all those green bars you were throwing away, you're glad you did because you were losing money on them. And this is an underground gold mine in Quebec. It's amazing how few rocks contain valuable metals and how much are they just happen to be close by. It's also amazing that in this case, XRF is able to tell us based on things like copper, lead, and zinc, and titanium, which of these rocks probably have gold in it, and it's usually right. Subtract off the operating costs. Here, the operating costs aren't that high, so the impact is a little less profound, which is an important thing to consider. Whether ore sorting works or not isn't just based on can you tell the difference between ore and waste. It's based on what are your mining costs, what are your milling costs, what are your production rates. There's a lot of variables that go into this, which is why we always build an economic model now. If you don't build an economic model, we find terrible decisions end up being made. So we always build that model, and then we let that model tell us where to take it from there, what the next steps are. So what are the tests? How do we prove ore sorting works? Well, we start with a preliminary test program, so 200 to 400 small rock samples. This is often very drill core, 1-inch pieces of drill core. We will scan each of those, we will assay each of those, and that gives us a wonderful data set to build algorithms to predict what's your recovery going to be. And now it's obviously based on a sample size that's far too small to be considered representative, but it gives you a lovely algorithm and good confidence in that algorithm. So you're not shooting blind guessing which algorithm you should use. Then you quickly as you can, you move into phase 2 where you get a larger sample size, measured in tons often. And that gives you confidence in that algorithm. It gives you confidence in your grade recovery curve. It doesn't give you as much data, but now it's something you can use in a bankable feasibility study or a detailed design. And that's what this one is here. Also, we increase capital cost and operating cost estimates as the studies progress. And then additional work in addition to the CapEx, OpEx of the sorting system, quantifying the work index, quantifying extraction recovery. A lot of the extra work will tend to be looking at different zones. If you have multiple zones with different associations, it could be worth having separate algorithms for each zone, and that's fine. But you'd need to analyze the data separately. So modeling, reserve calculations, and the mine plans. So when you do your block model and then you apply ore sorting to it, things can get a little tricky. You end up in a situation where you're throwing away waste, which is great, but now each block will have its grade change by a different amount. It's not like they all double. Some of them will go up by 100%, 200%, but some might only go up 10 or 20% because they didn't have a lot of waste to reject. So carefully looking at the block model becomes very important. especially for the mine plan. The mass of each block will change differently. The work index of each block will change. The extraction recovery of each block will change. And this is a lot to try to predict with pen and paper. So it's like, it's lovely that we have computers now and we can make them do all this work for us. That's what we talked about there. So questions about all these slides?
Yes. Thank you, Brent. Yes, there are some questions. So maybe I should, okay, I'll ask you a couple of them. So one question is about the maximum capacity throughput for ore sorting equipment, and if magnetite can be detected by ore sorting technology.
Magnetite is extremely easy to detect by ore sorting technology. Yes, you can use EM, optical, XRT, of course, because of the density difference. So yeah, that's one of the easiest. Tonnage per machine for particle sorting, you're looking at about 200 tons per hour still. I'm looking forward to 300 or 400 tons per hour, but I don't know if anything official has been announced. They're working on it as fast as they can. Bulk sorting, no real limitation because it looks at your entire conveyor belt. So yeah, if you're doing a few 100,000 tons per day, that's no problem for bulk sorting. For particle sorting, you know, a 10 pack, 200 tons per hour per machine times 10 is a respectable tonnage. Also, not everything you mine gets sorted because there's the fines bypass. So those fines can go straight to your mill and they don't need a sorting system. So there's things to consider there.
Okay, perfect. Next question is actually came in, could we detect silicates on iron ore?
Yes. Yeah, again, iron ore is one of the easier ones because you've got the density difference, there's a lot of tells in terms of the grade. Yeah, the challenging ones are things like, you know, gold and platinum, where you might not be able to measure directly the difference. But any sort of iron or base metal or magnetite, diamonds, those tend to be the easier sorts. Although the funny thing is, most of my work is in the gold and the platinums, the really challenging stuff. So, more questions?
Yes, there's another one. So, how are you characterizing historic low-grade stockpile?
Can you ask that again?
How are you characterizing historic low-grade stockpiles?
How are we characterizing?
Maybe we need to clarify this question a little bit further.
Well, I can talk a little bit about the low-grade stockpiles and the work I've done.
Yeah.
So they're probably my favorite application for ore sorting because, I mean, the historic waste piles and low-grade stockpiles, the more historic they are, the higher the grade tends to be. I took a waste pile in British Columbia. It was 0.8 grams per ton, which is reasonably high, except there wasn't a mill anywhere nearby, so they couldn't reprocess it. We ran it through the ore sorter, concentrated the sulfides, and next thing you know, in the lab, we got 8 grams per ton. In the field, we got 6 grams per ton. 6 grams per ton, that's worth shipping a little distance for processing. Lots of waste piles and lots of test work has been done, and not just by me, by others too, showing 10-to-1, 20-to-1 upgrade ratios can happen. It depends on your geology. But yeah, just picking out those 1 out of 10 rocks in the pile that have a lot of target metals. Yeah, there's a lot of potential there. And the great thing about it being a waste pile or a low-grade stockpile is management's expectations from that are minimal. So if you can say, hey, look, we created 100,000 tons of high-grade ore when once there was nothing. That's a clear win. So it's my favorite application.
Okay. So we have another question came in. What about the manganese?
Manganese?
Can
Yeah.
we do something? Yeah.
Yes, absolutely. That's another one that's relatively easy.
Do you want to elaborate on that a little bit more, or?
Let's see. You can use XRT, XRF. In some cases, you can even mess with some of the other sensors, but either of those will probably be the winner.
Have you done any projects on that specifically?
I have done one, yes.
Okay, perfect. Okay, so for now, I think we wait for more questions, and I am going to thank you very much, Brent. So, us during the whole course, and he can answer more questions as well, and he can jump in when Christine is also Christine is also going through the simulation, and then we can come back to the questions again in maybe in 10-15 minutes. So let's change the presenter now. Perfect. Yes, Christine, we can see you. You can share your screen. That would be great.
You can see my presentation now.
Not now, not yet. And thank you, Christine, for being with us at 5 a.m. your time. She's in Vancouver, so British Columbia. Same as Brett, actually. Let me request again to just show your screen.
I have it selected. It's just saying stopped for some reason.
And just two things. So one is while Christine is dealing with this technical issue, we will have a survey at the end. Feel free to ask questions while we're doing the presentation. And at the end, there will be a survey that we will send you, please. It will help us a lot on the follow-up if you want to have any follow-up, and also to understand how we can do this course better. We are able to provide the follow-up courses as well. We have another question, Brent, for you. So we can
Happy to, yeah.
Yeah, so it's a follow-up question on the manganese, and the question is, can manganese separate from iron?
So yes, definitely. And you've got some options. I mean, if it comes to it, you've got XRF, which looks at the elemental makeup. So you can sort based on manganese or on iron. Although that's not always my first choice, I'll probably look at, first choice might be density profiles with an XRT technology, dual energy X-ray transmission. Also color, well, maybe not color, but actually electromagnetic. This might be one of those applications where EM works nicely. Really, it would pay off to have a 10-minute chat with the project geologist and just chat about the ore. What are the characteristics of good rocks? What are the characteristics of bad rocks? And usually from that, I'll make a top 3 list of sensors we want to try. So I say, look, XRF, XRT, and laser. Let's try those, put together some algorithms, put the algorithms into the economic model, and then let the economic model tell us which of these is the right sensor for the project.
Thank you, Brent. We do have a question about the simulation while Christine is still dealing with her laptop issue. And the question is, how does IDEAS differ